Hey guys, welcome to Module 7, post-exam 2, which we had correlations, regressions, and t-tests. So Module 7 is kind of picking up around the t-test arena, which you will see once we get to our decision tree. But today, or this week, we're primarily going to be focusing on one-way and two-way independent ANOVAs. Past this, we'll be looking at repeated measures, one-way and two-way ANOVAs, and then after that, we'll look at the last type of ANOVA that we'll be covering for the class. So this is the home stretch. A lot of our concepts that we've talked about previously are going to be repeated now, so hopefully things start to sink in and they click. But I thought that this meme was really funny because ANOVAs are just building on t-tests. So you understanding t-tests is like you and a cat, as a cat in a corner, and then we add in ANOVAs, and then you're just like, no, t-tests. Anyways, hopefully you got a laugh out of that. I won't know anyways. But here's our decision tree. So we've covered actually a lot of ground so far in terms of what we've looked at in the decision tree, and our last set of tests are kind of going to be clumped in this bottom right hand corner of our flowchart. So for today, we are focusing on when we have a parametric dependent variable, a non-parametric independent variable, so not too different from our t-tests. Okay, and then we're going to go two different directions. So one-way ANOVAs have one independent variable with three or more levels. So that's how they're different from t-tests, right? T-tests had two levels of the independent variable. ANOVAs will have three or more. And then similarly, if we have a between subject factor, we would have an independent ANOVA. Oftentimes it's just referred to as a one-way ANOVA in SPSS. And then if we have a within subject factor or a within subject independent variable where our samples have been measured for each of our independent variable levels, that would give us a one-way repeated measures ANOVA. If we have multiple independent variables, so two or more, that will take us into what we call a factorial ANOVA, which has three different options. We're going to cover the first option this week. So this is where you would have two between subject independent variables. In other words, every single sample that you've collected, everyone is only sampled one time. Okay. And then our other factorial ANOVAs, just so you are aware of what they are, instead of two between subject variables, we could also have two within subject variables, which will take us to a two-way repeated measures ANOVA. And then we might have a combination of both a between and a within subject variable, which will give us a mixed two-way ANOVA. Okay, so this is where we are in our course map, pretty much. If we look at the decision tree in a slightly different way, again, we can see for independent ANOVAs specifically, I've kind of highlighted what we're focusing on, and then next week we'll flip to repeated measures. But we have a parametric or ratio or interval dependent variable, and just one. Okay. Our independent variable is going to be non-parametric in nature, so for our class it will always be nominal. And then we can branch. If we have one independent variable that has three or more levels, it is a between subject factor. That tells us we're going to have, and I should have changed that to type of ANOVA. This will give us a one-way independent ANOVA. Okay. If we have two independent variables, we only need two or more levels of each variable. You could have three or more, but you need at least two levels for the ANOVA to work. And then both of those are going to be between subject factors. That would tell us we do a two-way independent ANOVA. Okay. In the cases where you have within subject variables, that's when you do repeated measures, which is very similar to a paired samples t-test. Okay. So independent ANOVAs are pretty much an expansion of our independent t-tests. We're going to be reviewing concepts from t-tests. So with that being said, let's talk about what the goal of an ANOVA is. First off, what does ANOVA stand for? It stands for Analysis of Variance. Okay, and so basically the main function of an ANOVA is very similar to a t-test, right? We're trying to establish a cause and effect kind of relationship between variables, where one manipulated independent variable is causing an outcome of a dependent variable of interest, right? And if we want to examine the differences between 3 or more group means, that's when we run a one-way ANOVA. If we want to examine the difference between means within each independent variable as well as interactions between independent variables, that's when we would run a two-way ANOVA. Okay. When we're determining the statistical difference between means, we are going to calculate an F-statistic. So when we did t-tests, we calculated t-statistic. We looked at the difference between the means and the numerator, divided it by some type of error, right, or standard error. In that case, it was standard error of the difference. Similar calculations will happen for the F-statistic, where we're looking at different components from our group measurements, divided by some degree of error, and then we end up getting a statistic. Now we could compare this to an F table or critical values within an F table and estimate p-values kind of similarly to how we estimated p-values for t-statistics. For this class, I decided to cut that out this semester because you guys already have enough to remember. But I do want you to understand how the F-statistic is calculated, and it'll be different for an independent ANOVA versus a repeated measures ANOVA. So the general concept of how we get the F-statistic is kind of similar, but the way that we calculate certain components of calculations that go into the F-statistic are going to be slightly different. So without further ado, you guys may have noticed in your regression analyses or outputs that you would get the ANOVA table, and that's where we determined if a regression analysis was significant, or if the independent variables that were in the model significantly predicted the dependent variable. Now, the layout of that ANOVA table is the same as what you will see in the next several weeks, but the actual components of the ANOVA table are going to mean something a little bit different now, and we're going to focus on what each of those means. So for between subject, or when you have a between subject sample, you will get an ANOVA table in SPSS that looks something kind of like this, where you have a row that is for between groups, you'll have a row that is for within groups, and then you'll have a row that has totals in it. Now, I don't want you guys to get confused with between groups, within groups, and between subject and within subject. They are different things, okay? So between subject and within subject are terms that we usually will use to describe the type of independent variable that's being used, or the sampling method that's being used, right? Whether we're using independent samples or if we're using the same sample and measuring those people multiple times. That is very different than what the ANOVA table means. So between groups in this sense, or when we're calculating the sum of squares specifically, is going to look at the sum deviation of each group mean from kind of the grand mean, or the mean of all of the groups. So if we had a single dependent variable measure, and we took the mean of every single measure, that it doesn't matter which group people are in, but we just took a mean of all of the dependent variable measurements that we've collected from our total sample. And if we took a group mean, so let's say sample A, we took their mean, we subtract the grand mean of all of our dependent variables put together, or dependent variable measurements put together, and that is the deviation. That's a between group deviation. So for however many groups we have, we would do that group mean minus the grand mean, sum that together. Well, there's a little bit more that actually goes into that, but we take the sum, and that gives us a sum of squares. Okay, so that's what SSB, or the SS for sum of squares for between group comparisons, is calculated. And then the within group calculation is going to look at, let's say we have 10 people in sample A. For each raw score, or each subject in sample A, we take their score, or their dependent variable measure, subtract the group mean that they belong to, and then we sum up all of those. And that ends up giving us our sum of squares for our within group comparison. Okay, so between groups is looking at different groups compared to the grand mean of our total sample size. Within groups is going to be looking at the deviation from single raw scores and how they deviate from the group mean that they belong to. If we go down a row to our total row, that'll just be the sum of squares of our between group comparison plus the sum of squares for our within group comparison. And we end up with sum of squares total. We don't actually end up using this value, but just so you know where it comes from. We also have a degrees of freedom column, and the degrees of freedom are going to be calculated slightly differently. So the degrees of freedom for between groups is going to consider the number of groups that you've collected. So usually in ANOVA you'll have at least 3. Okay, and we would say in that case K would represent the number of groups. So 3 groups minus 1 gives us our degrees of freedom for the groups that we've collected, or the samples we've collected. For within groups, we're interested in the total number of subjects that we've collected. So let's say we had 30 people, 10 people in 3 different groups. Okay, so we would take 30 and then subtract the number of groups that we have, and that gives us our within group degrees of freedom. Okay, from there, again, you can reference your total degrees of freedom by looking at your total sample size minus 1. And then using primarily these 4 squares here, so between and within sum of squares and degrees of freedom, we can calculate our mean square. So for mean square, you basically calculate across the row. Okay, usually you'll be given at least the sum of squares. You will have to, you will be given a table at some point, especially for exam 3. We'll have a practice run in your activity this week. But you'll have at least a sum of squares given to you. And then from there, you would be able to calculate degrees of freedom based on sample characteristics. And then from there, you can calculate the mean square. So the mean square for between groups is going to be the sum of squares divided by the degrees of freedom for the between group comparisons. For the mean square of within groups, it's the same thing, but you're using sum of squares divided by degrees of freedom for the within group comparisons. From there, to get our F-statistic, also called our F-ratio, we take the between group mean square value and then divide it by the within group mean square value. So usually this F-statistic could be, like I said previously, could be compared to a critical value on an F-table to estimate a p-value. Lucky for us, SPSS will give us a p-value that is calculated within the software. And that's usually going to be included in another column next to the F-ratio. Okay, but that kind of breaks down everything that goes into calculating the differences between 3 or more means. And the next thing I wanted to talk about is the difference between independent one-way and two-way ANOVAs. So if it wasn't made clear in the flowcharts or decision trees, the primary difference between a one-way and a two-way is the number of independent variables you have. So if you can identify one independent variable, You pretty much just need to figure out, is it a between subject or is it a within subject factor? And then that tells you what type of one-way ANOVA you're working with. Okay, so we're only looking at the differences between groups of a single independent variable. For two-way ANOVAs, in like some research scenario, you would be able to identify two primary points of comparison, right? So either independent variable A or independent variable B, okay? Two-way ANOVAs are also referred to, or at least independent two-way ANOVAs can also be referred to as two-way between ANOVAs, two-way independent factorial ANOVAs. I also have this numbering convention where the numbers represent the levels of each independent variable. So let's say you had 3 levels in one independent variable and 5 levels in another one. You could say it's a 3x5 independent ANOVA or a 3x5 between ANOVA. You can mix the wording as long as you have something that indicates you have 2 independent variables. So either using this level by level naming convention or the two-way naming convention, and you have something that's indicating the types of independent variables, then you pretty much have the naming of the test that you're using down. So either you'd have between or independent somewhere in the naming convention, in addition to the two-way or the level-by-level comparison. Okay, but the primary difference here is that we're going to be looking at not only the effects of each independent variable individually, right? So let's say we had independent variable 1, we would look at all of the measurements for independent variable 1 regardless of independent variable 2. We could also do the same thing for independent variable 2, right, and look at all of our measurements for that variable regardless of the first independent variable. And then the other thing that we're adding in two-way ANOVAs is an interaction effect. So not only are we interested in the individual main effects of each independent variable, but we also want to see how each independent variable might affect the other independent variable. So maybe we have males and females, and we collect males and females for different sports, right? So we have identified 2 different independent variables that are between subjects, and maybe we want to look at the differences between males and females for a certain dependent variable measure within a certain sport, right? And then the two-way ANOVA gives us that ability. So that's why I was saying you don't always have to have 3 or more variables in a two-way ANOVA. As long as you have 2 independent variables with at least 2 levels each, that allows you to look at the interaction effect between those independent variables. For one-ways, you have to have 3 or more. Otherwise, you would just be running an independent t-test. Okay. For the assumptions, they're pretty much the same as an independent t-test, so you have to have random sampling. Make sure you get a nice representation of your population of interest. You should have a normal distribution with no significant outliers for the dependent variable of each group. So this is very similar to the explore analyses we did at the beginning of this semester where we used a split file command. So let's say we have males and females, right? We might want to group our explore analysis by gender or sex, and then we can look at our descriptive statistics for each male and female for the dependent variable to see if we have normally distributed data for both of those. Okay. The rest of the characteristics are pretty much based on the study design. So you need a single dependent variable that is ratio or interval data, parametric data. And then your independent variable characteristics are going to be dependent on the type of ANOVA that you're running. So if we're doing a one-way ANOVA, you would have 1 between subject independent variable that is nominal with 3 or more levels. If you're doing a two-way ANOVA, you would have 2 between subject independent variables that have at least 2 or more nominal levels. Okay. In each case, because we have a between subject variable, we still will be looking at homogeneity of variance, which is similar to an independent t-test, and we'll still use Levene's test to look at that, right? Now, the way that this is set up in SPSS will be different than an independent t-test. It'll still be listed as Levene's test of equal variances, and the general null hypothesis of the p-value that you get for Levene's test is the same. We're just adding on another grouping, right? So the null is still going to say that there are equal variances between groups. In this case, we just would have group 1, 2, 3, maybe 4, and so on and so forth. I do want to make a special note about homogeneity of variance, because the way that we can proceed our analysis in SPSS is going to be a little bit different between one-way and two-way ANOVAs. So for one-way ANOVAs, take a step back. In t-tests, we had it nicely laid out in our output. Whenever we had violated Levene's test, there was already a correction built into the t-test. So we had an equal variances assumed row, and we had equal variances not assumed row, and then based on if you met or violated Levene's test, you knew which row to read, and that told you which p-value to accept. We don't get the same thing for one-way ANOVAs. So if we violate, right, so if you meet your assumption, you're good to go. Read the ANOVA table for the main effect, and you can move on with your interpretations. However, if you violate Levene's test and we do not have equal variances between our groups, we have to apply an adjusting factor or a correction to our degrees of freedom, which is using Welch's test. That will make more sense when we go through how to make the test and how to read the output. But essentially, the p-value in Welch's test is interpreted exactly the same as the p-value in the ANOVA table. They will not always be the same. So when you're doing your activity, make sure that you have a stepwise fashion on how you go through your procedures. Check your assumptions, and then that tells you which p-value to accept for the different ANOVA tables that you'll have. You either have the main ANOVA table or you'll have the Welch's, I don't remember, it's like robust something. But you'll have a Welch's table or the ANOVA table, and you'll read each one based on if you've met or violated homogeneity of variance. Okay. For two-way ANOVAs, it's not so simple. So if you meet your assumption for homogeneity of variance, that's fantastic, and we can go to the ANOVA table and then read all of our main effects. So that's nice and easy. However, if we violate homogeneity of variance for at least one of our independent variables, then that's where it gets a little bit messy, right? So violation means that at least one of our group variances is not equal to the other variances within our other groups. So there is kind of some limitations in SPSS where we can't apply certain correction factors that usually would take care of not having homogeneity of variance, but we don't have those resources available to us. So there is kind of a loophole, if you will. If your sample sizes are relatively equal to each other, and each sample size is about 30 or more, so you have relatively equal sample sizes that are large, and your largest group variance divided by your smallest group variance is less than the value of 3, you can reasonably say the ANOVA test is probably robust enough to account for any differences in variances between groups. So in that case, if we kind of meet that criteria, we can go ahead and read our ANOVA table and assume that the test is robust enough to take care of the violation, or such that the violation doesn't affect the results of our test. If, however, both of these things are not true, for our class, we're going to proceed with caution and kind of just note like, hey, this was an assumption we were supposed to meet. It got violated. These were the results that prove it was violated. These are the results that show that we might not have good data to like keep going. That's what we'll note in the activities, but proceed with caution. Still go through all of the examples just for the sake of going through and reading or learning how to read the outputs. Usually, though, in like a real research scenario, we would want to reevaluate the data. Maybe we have an outlier somewhere that didn't get picked up, that wasn't maybe a significant outlier, but it caused a large enough degree in variance that that's what caused the violation. Right, so we might have to reevaluate the subjects that we've included, see if we need to include more subjects, see if we need to toss out subjects, right? Just reevaluate the data, figure out if there's a way that we can combat any of the issues that we're running into, and then see then if that fixes the homogeneity of variance problem. So again, the way we treat this assumption for both one ways and two ways is different, but essentially they're still looking at the same thing. Do you have equal variances between your groups or do you not? And then what do you do after that? All right, into our hypothesis testing. For one-way independent ANOVAs, let's say we've met all of our assumptions and we now have gone to our ANOVA table. Okay. Usually when we're looking at a one-way ANOVA, the research question is investigating if a 3 or more level independent variable has a significant effect on a dependent variable. So that brings us to our non-directional hypotheses, where our null hypothesis is going to argue that the independent variable has no significant effect, versus the research hypothesis will say there is a significant effect. Okay, and we can visualize this very similarly to our t-tests, where we say that all of our means are equal, or at least one of our means is not equal to the others. Okay, you could also phrase this as there are no significant differences in the dependent variable between means of sample A, sample B, and sample C. Okay, so the wording is very similar to t-tests, we just are adding another level. As far as statistical significance or determining if we have significance, we're just going to focus on exact p-values that are provided to us in SPSS. And these are going to be from the ANOVA table, assuming that we've met our assumption of homogeneity of variance. If not, again, we would look at the Welch statistic, but the interpretation of that is going to be the same as from our ANOVA table. So if p is greater than alpha, in our case 0.05, we would accept the null hypothesis per usual, and we would argue that the independent variable has no significant effect on the dependent variable. If, however, we get a p less than alpha or less than 0.05, we would reject the null hypothesis and say there is at least one significant difference between two of our independent variable groupings. Okay, and I put a star here because we have kind of a follow-up on the next slide. If you have a p less than alpha, because we have 3 different groups, there's potentially 3 different comparisons that we can have between each of those groups, and our ANOVA is just saying at least one of those pairs is not, or one of those pairs of means is not equal. Okay, so in that case, we need to do some follow-up tests or post hoc tests, also referred to as pairwise comparisons. And these are basically glorified t-tests between each possible pair of independent variables. So if we had a 3-level independent variable, our post hocs would be comparing independent variable 1 and independent variable 2, either saying the null arguing they're equal, the research hypothesis saying they are not equal. We would compare independent variable 2 with independent variable 3 and independent variable 1 with independent variable 3. So those are all of our possible pairwise comparisons that we can make between the 3 levels of our independent variable. Obviously, if you have more levels, there are going to be more comparisons. But in each case, the null hypothesis, because you'll get a p-value for each pairwise comparison, the null hypothesis says that the means are equal. The research hypothesis says the means are not equal, right? And then from there, you can interpret the p-value as if it's greater than 0.05, there's no significant difference between those two independent variables that were paired together. If there is, or if you have a p-value less than alpha, then that would mean there is a significant difference between whatever two independent variable levels you have paired together. Okay. I just added this meme of Ryan Gosling, because who doesn't like Ryan Gosling? And it says, "Hey girl, let me run a post-hoc test on your one-way ANOVA." Anyways, I'm so funny. That's one-way ANOVAs in a nutshell. We'll go through this in our SPSS stuff, so it's very procedural, and we don't really deviate from that procedure. Check assumptions, check your main effect, check your post-hocs, and that's it. Okay? It sounds a lot simpler when we say it that way, but yeah, we're adding a lot of p-values this week. If you thought the regression was crazy, this is crazier. The nice thing is the interpretations for all the p-values that you're running into. You've kind of made those interpretations before, or you're expanding on those interpretations. So hopefully it makes it a little bit easier than regressions, because the interpretations from those were all different. All right, so that's one-way ANOVAs. For two-way ANOVAs, we get a little bit more complicated, because statistics likes to do that to us. So in a two-way independent ANOVA, recall that we have two independent variables. At the beginning of the lecture, I was saying that you have kind of three main things that you can do with these two independent variables. You can look at them independent from each other, right? So just looking at a main effect for independent variable A, or just looking at the main effect for independent variable B, right? In which case, that would be very similar to a one-way ANOVA, where you're saying this particular independent variable has no significant effect on the dependent variable, but you're just specifying which variable you're talking about. Okay. In addition to each main effect of each independent variable, we can also look at an interaction effect. And I put this on another slide so that we have some room to expand, because the interaction effect is where things get crazy. So just for reference, you are going to have three p-values that you report as the main effect of a two-way independent ANOVA. Okay, you have one for independent variable A, one for independent variable B, and then one for the interaction effect. Okay, so for the interaction effect, it's mainly saying independent variable A has no significant interaction with independent variable B. As nice, simple null hypothesis. The actual interpretation of it is not so simple, so I apologize for that. But when we have a significant interaction, we will go through and do some crazy stuff in SPSS where we regenerate the output so that it includes two different types of interaction comparisons. We can either look at independent variable A within levels of independent variable B, in which case these are kind of the null hypotheses that we would assume, right? So within group 1 of independent variable B, we can see are the means of all of the levels of independent variable A equal to each other. And then we would do the same thing for level 2 and 3 of independent variable B. So this would be like if we had different sports and different stages of learning. So let's say we have basketball, football, and soccer, and we want to look at, I don't know, sprint speed between novice, intermediate, and advanced individuals. right? The novice, intermediate, and advanced or experience level is a between subject independent variable. And our sport, assuming that people aren't coming from the same sport, assuming people aren't coming from, they're coming from one sport only. Words are hard sometimes. But that would also be an independent variable. So we have an effect of sport and we have an effect of experience. Okay, so we could say within, let's say, independent variable B is our sport. So let's say within basketball, are there significant differences between our experience levels? Right? Is there a significant difference in sprint speed for novice versus intermediate versus advanced? Okay, and that would be a very simple way to put that, other than looking at a bunch of numbers and letters. We could do the flip of that as well and look at the sport, in our case independent variable B, right, within independent variable A, which is our experience level. So instead of saying within basketball, what are the differences between our experience levels, we could say within all novice players, what is the difference between basketball, football, and soccer? I'm pretty sure those were the sports that I started with. But that would be another way to look at an interaction effect. Okay. So when we look at p-values for these, which there will be a lot, primarily we're starting with the main effect from the ANOVA table in terms of significance, which we've kind of already talked about for main effect A, or for A and B, which we go back. I have a lag. There we go. Right, we have main effect A, main effect B, and an interaction effect. So when we were determining significance for each of these, for main effect A, it will be listed as its own variable. So let's say we'll stick with the sport and experience level example, right? We said experience level was A, so we just want to see for our sprint speed dependent variable, regardless of what sport people are in, are there significant differences between novice, intermediate, and advanced players? Okay, if we have a p-value that is greater than alpha for this independent variable, that would mean that experience level has no significant effect on our dependent variable, sprint speed. If, on the other hand, we have a p-value that is less than alpha, we reject the null and say there's at least one significant difference between our experience levels, in which case we would want to do our post hoc tests to see where that difference exists. So we would compare, say, novices to intermediate, intermediate to advanced, and novice compared to advanced. And then we get p-values for each of those, and then we say, is there a significant difference between each pair, or is there not? Okay. We would do the same thing for the main effect of independent variable B, which is our sport, in the example that I'm running with here. Okay, so if we have a p-value less than 0.05, sport has no significant effect on sprint speed. If we had a p-value less than alpha or less than 0.05, there's at least one significant difference between the sports, okay, for the sprint speed that we measured. So then we'd look at post hoc tests, and we'd say, is there a difference between basketball and football, football and soccer, or basketball and soccer? We get p-values for each of those pairwise comparisons, and then we can determine, do we accept the null and say there's no significant difference between those pairs, or do we reject the null and say that there is a significant difference between the pairs? Okay, so that's for our independent variables, or the main effects of each independent variable. The pairwise comparisons is where we get fun. Yay! Internal crying. So in the table, this is going to show up as independent variable A with an asterisk B. So it's kind of like saying A times B, or looking at the interaction between the two. Okay. In the ANOVA table, if you get a p-value that is greater than alpha, there's no significant interaction, you stop your analysis there for the interaction effect. You are good. Okay. If you get a p-value less than alpha, that's where we have to do some fancy stuff, and that would tell you there is a significant interaction. So then we look at pairwise comparisons to figure out where the significant interaction exists, right? So this is where I was saying it helps to visualize a little bit differently, right? If B, or independent variable B, is our sport, we're saying within one sport, are there significant differences between experience levels, right? So we have all of these comparisons. Each of these is going to have a p-value. Then we evaluate the next sport, and we say, well, in this sport, are there significant differences between experience levels? We get a bunch of p-values. We do the same thing for the last sport, and then we've kind of got our comparisons for this interaction, or the way that we can view that interaction. We can then view it the other way, and say if independent variable is looked at within levels of independent variable A, the post hocs would then look something like this. So instead of sport, we would say within novice players, are there significant differences between sports? Within intermediate players, are there significant differences between sports? And within advanced players, are there significant differences between sports? Okay. Again, this will all make more sense when we start applying some examples, but this is kind of your go-to reference when you're doing your activity for wording specifically, right? So once you figure out what your variables are, you can say, all right, well, I know I have a one-way. What's the null for a one-way? Find the slide for the null for the one-way, and then just plug and chug your variables. And hopefully by the end of the activity, it'll make more sense. Okay. And then my last meme, just to bring it all together. First you were holding on to t-tests, and then once you understand ANOVAs, you're just going to be like, damn it, factorial ANOVAs, because they are a lot more complicated. We stop at two-way ANOVAs for any of you who are interested. There are also three-way ANOVAs. I've seen as many as a four-way ANOVA in research before, but as you add more variables, you add more interaction effects. So for a three-way ANOVA, instead of having three main p-values that you're looking at, right, for each independent variable as well as the interaction, you're also going to be looking at a third main effect plus the double interactions plus your three-way interaction. So you actually end up with 7. Right, so going from a two-way with 3 p-values to a three-way with 7 p-values, you can just imagine where a four-way takes you. So anyways, that's kind of like the fundamental concept lecture. The next 2 lectures are going to be on the SPSS procedures, so hopefully those will be a nice reference for you when you're going back through your activities. All right, I'll see you then.